fun. This is my fun. Is making my students, bribing my students to dress up for a costume party. And then we'll do a picture at the end. We'll do a picture, a group picture of everybody. Should we do a group picture right now? Let's do a group picture right now. Yeah. So it's kind of like group in right here. Group in right here. Yeah, we'll let you do it. I'll have you also take one. Also have to take one. Well, you get in there first. Just like. Come on, just. Yeah, there you go. You're going to have to like double up. You're going to have to double up a little bit. You guys get over here. You can, even if you're not dressed up, you can get in. Come on in, guys. Tennis player. Nice. We got Top Gun, or we got. Why is everything tough? What is it? Superman. Funny kid. Here we're doing a picture quick, guys. Do a picture quick. There, Beth, I see you there. Yeah. All right, we're waiting on you guys. We're waiting on you guys. Even if you don't have a costume, you can get it too, because you showed up today. Okay. All right, you guys aren't grouping together very well, but that's all right. Get in there, everybody. So you got to be able to see the camera. If you can't see the camera can't see you. All right, here we go. Here we go, guys. Focus. Big hair guy. There we go. All right, here we go. All right, 1, 2, 3. Yeah. Okay, then I'm gonna do one more.
I can take it.
No, I got it. I'll do this.
I have no incentive to be in this photo. Oh.
We got construction. Construction person. You're gonna have to go over here, Julia. All right. Yeah. Julia, further. We gotta go over. You gotta go over. Just there we go. All right, 3, 1, 2, 3. Yeah. Okay, got it. All right, thanks, guys. Thanks for participating. It's awesome. Remember what I said? Just let this nerdiness wash over you. It's time. All right. So the exam is on Friday, right? Everybody knows that you're here. I gave you 2 example problems. There's 2 problems. There's one kinematics problem, right? This is our kinematics problem, taking a step from one point to another point, working our way around. Something to keep in mind is we don't have time to do a sun gear or like whatever that other one was, a little half one with the thing going around with like 5 different members, and we did accelerations and it was like 2 pages of calculations. Well, we don't have time for that, right? So we only have time to do a couple little things, probably mostly velocities, because the concept is the same for accelerations, but velocities we just have a little less complicated to step our way through, and the process is very straightforward. You just follow that process. It's going to lead you to the right answer, with the exception of maybe making a small mistake on signs, making a positive versus a negative or something like that. Other than that, you should be able to get most of the points just by working your way around. Okay, and then a very, very structured way to do this. And I think talking to most of you, most people are okay with these problems, right? And that's one of the kinematics problems, right? This is probably a little on the long side, just because remember these came from 2020 when they were take-homes and they're 50 minutes, and we only have 25 minutes, but if you can do this, you should be okay, right? And then also there'll be a kinetics problem, F equals MA problem, okay? And then we'll go through both of those. So with this guy right here, right? Hopefully you had a chance to work it out yourself beforehand. If you didn't, that's okay. Maybe afterwards you can try to do it by yourself after I kind of show you. But it is important to try to do things. Again, where I get these problems is I open up a textbook. This one I made up, but usually I just open up a textbook and I look through it and I find one that I think is doable. I do it, make sure I can do it. I modify it slightly, make it easier or harder depending how long it took me to do it, and then go from there. So when you're studying, you can just do that. Open up your textbook and find a problem near one of your homework problems and see if you could do it, okay? All right, so to do this problem, right, what we're gonna do is, right, the process is we're gonna start out at a point that we know something about and take a step to something that we wanna know something about, okay? And so in this particular problem, they tell us that the velocity of point C is 20 feet per second to the right, right? And what we're asked to find is the angular velocity of the bar omega AB, the velocity of point A is another one, right? Just those two things actually is what we're asked to find, okay? And so it shouldn't be too bad. Where should we start, or where could we start? Because I know that 20. I absolutely can. I can start there, right? What other point do I know something about? D, right? What's the velocity of D? Zero. Okay. The way I did it and the way my solution is, I'm going to stick to that just so I don't have to. You saw me do math earlier today, right? And so, but I'm going to go from D to C, right? And I know it, right? Because I could do that. I take a step from D up to C, and then I know what the velocity at C is, and out of that I should be able to get omega. Right? I should get omega of this disk, right? Once I get the omega of the disk, then where can I go? I go up to B, right? I can go up to B once I get omega of the disk, and then once I get to B, then where can I go? Down to A. What you can't do, and when I see somebody do this, I see somebody do this every exam, right? Every year I give this exam, they try to go from D to A, just like in one fell swoop. I can't do that. Why can't I do that? They're not on the same member, right? D and A aren't on the same member. I can only do that stepping from from the same member. I could go D to B, I could go D to C, I could go C to B, I could do anything there, but in order to take the jump over here, I have to use this bar, because that bar is connected to the two of them. Okay, so just be careful. Don't go D to A. You can't do it.
If the bar was at point C, if it was attached to point C,
then I could go right from C to A. Yeah, and then that'd be a pretty easy one, right? If this is C, then it was just attached right there, then done, right? Because they're attached, and they wouldn't be. Yep. Maybe I'll give you that. Maybe I'll give you that one. Yeah, you'd appreciate. Okay, so let's do this. VC. I like the acoustics in this room. Good acoustics, huh? I like the big concrete columns and beams, right? As a structural engineer, can't see outside. Not distracted by the outdoors. VC is equal to VD plus omega C crossed with R. C is seen from D. Is Isaac here? Isaac didn't come today. Oh, he's changing. He's changing. Right? So I'm gonna go 2C from D. Right? VD is 0. Right? That guy's 0. Right? And then I know what VC is, right? VC, right, is 20 in the I direction, right? I do know that, right? Because that was given to us. There was 20 right here. That was 20, right? So let's just kind of expand this out. So 20 in the I, 20 in the I is equal to omega, we'll call that omega C in the K direction, crossed with 5 in the J. Okay, I see someone coming in. He's going up over here. Is he nervous? You went all out, Isaac.
Yeah. Big dog over here.
Yeah, you have to wear that the entire time to get credit. we got George Washington Nice. It's impressive. Good job, guys. Isaac, you don't have to wear that the whole time if you don't want to, but it'd be really funny if you did. Okay. What's he saying? That's awesome, dude. Right? Again, just be careful of this. Like we've done this enough, but again, be careful of the sign of this, right? This R value, our C is seen from D. I'm going to C from D, and so it's that vector that's pointed up right there, right? And so that's the radius there is 5 feet in the J. Do I have to turn this to inches? Do I need to turn this to inches or anything? Do I have to worry? Not really, right? Because I'm not dealing with forces, and forces you want to leave it in feet anyway. But you know, I don't really have to worry about like changing units here. I can just leave it in whatever, because it is just, there's no forces involved, so the units don't really matter. So if this is in millimeters, I could leave it in millimeters. I wouldn't have to change it to meters, okay? And so it's 0 in the J direction, on the other side there. So then this, you carry out this right here. So I'll just do this. This, let me carry out that. That's going to be 20 in the I is equal to negative 5 omega C in the I. It's good that they both ended up in the I direction because they have to, right? I mean, they both have to end up in the I direction. If they didn't, then something went wrong, right? And then just be careful of that cross product. Come up with your best means of doing that, right? I like the right hand rule or my calculator, or you could do that circle thing, but just make sure you're understanding, why this came out to be negative. I got K crossed with a positive J, and so my thumb's pointing in the negative I direction, so it's negative 5 omega C in the I. And so I can get what omega C is. Omega C is equal to negative 20 over 5. I got to redeem myself here. 20 over 5, that is negative 4, right? Negative 4. I left it as 20 over 5 in my notes here, probably because I was nervous, right? So I got omega C now, right? I did the whole thing, right? I went through and I took a step from the bottom, right? Or you could do this, right? Or rolling wheel kinematics, right? VC is equal to negative R omega, right? That's the other way to look at it. It is just a rolling wheel, right? It's just a rolling wheel, and so I could just do R times omega and get to the same place. So if you notice there's a rolling wheel, you could come up with that relationship yourself, or you stick to the plan and do the steps from one point to the other point and get this, okay? I did not take into consideration everybody looking in at us. Right? We just had an audience there for a second. The other room that was open was up at the basketball court, but then lots of people could watch us, and I didn't want that. Okay, all right. So now I have this omega. Now what do I do? Now I know what this omega is, and it is rotating like this with 4 radians per second. What do I do now? Huh? Yep, I could go C to B, or I could go D to B, either one. Right? I personally chose D because that's 0. I went from 0 to B, right? Or D to B rather, right? I could go from C to B, any point from any point, right? And if I went from C to B, I would start out at 20 feet per second in the I. If I go from D, I could start out with 0. So I went from D. And so I say VB, because I need to get up to B. VB, right, is equal to VD plus omega C, right, crossed with RB, is that B? RB is seen from D. Okay, VD was 0. All right, and so this is equal to negative 4 in the K. That's my omega, and I cross that with 10 in the J. And again, be careful of your sign. I'm going from D up to B, and that is going to be 2 5s, which is 10 in the J. And it's positive 10 because I'm going from D up to B. Right? And so this ends up being equal to 40 in the I. All right, and that is feet per second on that. Which kind of like after we're there, it kind of makes sense, right? If this thing is pivoting around, point D and that's going 20, that should be going 40, right? It should be going twice what the center's doing because it's twice as far away from D down at the bottom. But again, I don't need to look at it and know that, right? I could just stick to the plan and making the steps. And then afterwards, like I said, I like to go back and say, stink test, is that okay? Yeah, it's okay, right? That makes sense to me to be twice what the center's doing because it's twice as far away from point D, right? And it's kind of rotating about point D, right? Cool. So now I know what point B is, right? And then I guess one of the key things there is the omega for this body is it's the same omega. It's, the omega point B is -4, omega point C is -4, and omega of D is 0.4. Any point on that body, it's all the same omega, right? And so there I'm going to go from B down to A, right? And so that's what I do. I say VA VA is equal to VB, which I just found, plus omega, what was it? Omega AB. Omega AB crossed with R, A is seen from B. Right? And what this ends up looking like, right? I got 40 in the I is what VB is doing, plus omega AB. I don't know if it's positive or negative, so I put it in there as positive, but I do know it's in the K direction. Okay? Omega AB in the K direction. And then I cross it with RA is seen from B, right? And then what that's going to be, again, it's going to be this. That guy right there, that vector. And so I'm going to the left 15 feet, and then I'm going down 5 feet. So they both should be negative because I'm going negative in the negative x direction, so negative 15, and then I'm going down 5. So it should be negative 15 in the I, minus 5 in the J. Isaac, you doing okay? You doing all right? You can hear me and everything?
Yeah.
Is there a little fan going in there? That's awesome. You go from not wanting to wear a costume to wearing that. It's awesome. just that. All right. Okay. So then what we do is just carry out that cross product, right? You carry out this cross product, this cross with this, and then this cross with this, right? And if you do that, you get this. So we have 40 in the I, that's still floating in there, minus 15 omega AB in the J direction, plus 5 omega AB in the I direction. Okay? The other thing I know something about the velocity at point A. What is the velocity at point A? Is it constrained at all? Right? It's only in the X direction, right? It's not going up and down, right? It's just going straight. It's going straight there because it too is just a rolling wheel, right? And so that's an assumption I can make down here. So let's keep going with this, right? We know that VA is in the I. Now at this point, you lump all your I's and J's together. So VA is in the I, and that's equal. And I lump my I's. I got 5 omega AB plus 40. Both of those are in the I direction, and then the only thing I have in the J direction is negative 15 in the J. Okay? And now at this point, right, what I like to do is just break it into the X's and Y's, right, or the I's and J's. I just got to break it into the two problems here. So if I look in the X, right, look in the X direction, I got VA is equal to 5 omega AB plus 40. And then the Y direction, right, Y direction, we get 0 is equal to negative 15 omega AB. Okay? That's the key there, right, is the right-hand side here, this omega AB. So this tells me omega AB is equal to 0. Okay? And then if omega AB is equal to 0, then VA is just equal to 40. Have a long journey over there, but that's it. That's what we were after. Right? It's kind of tricky because, and be careful of this. I noticed in the last exam, I asked this in two different problems, right? I said, or two different parts. What is VA and what is omega AB? They both came from the same process, right? So don't let that fool you. I noticed that happened sometime maybe on the last exam is I asked two parts to the problem, and then you think that you have to do more work to get the second part, but both of the answers came out of that one part. Yeah.
When you have your
Christopher, is that what you? Christopher Columbus, that's what I was going with. But Explorer, what do you got?
When you have the equation for in the I and J direction, should that negative 15J, should that be negative 15?
Oh, yep. I wasn't done yet. I was saying, what's missing from here? That's exactly right. I was just going to get to that. Right, I wasn't finished yet. That's a great point. Right? Did you everybody see that? I was missing it there. Right? It's this, I dropped the omega b off this term. And it's supposed to be there. It came back in down here. It came back in down there, but it should be right here. What I got in green right there. Okay, so just be careful of that, right? Sometimes both answers pop out of the thing. Okay, stink test. Does that make sense? Right? Is that okay that that has no omega AB? Think about what it's doing right before then, right? Right before then it's rising, right? Before then it's rising, and then it hits the top, and then it's going to start going back down again, right?
It only has an I coupler. There's no movement in.
That's right. Yeah, and it shouldn't do that way. And then it's also right. You see what I'm saying? Is it's going like this. It's rising up right before then, and it hits the top, and then it starts going back down. That's why it has 0 omega right at the top. It's peaking out. It's moving up, peaks out, and then comes back down. So it's up at the top right there, and so it shouldn't have an omega. And then it's going to go the same, that direction in the same velocity as B is going, right? And so it ends up being tied. Do you need to know that beforehand? No, right? Like I don't need to know intuition, right? Where kids run into problems is they're like, all right, so what's going to happen when this thing rotates? They try to think about that. You're trying to think about like, oh, is it going to go up and then it's going to start going down? And they start and they confuse themselves and stuff. And then, oh, this one's got to go the same speed as this one horizontally. You're not good enough for that. Right? I'm joking, but also serious. Right? That's intuition that you haven't had a chance to develop yet. And so I'm showing you the process to get to it without thinking too much. Right? Which is kind of weird to say, well, I'm teaching it, but to start out, you don't have the skills. The longer you do this, then you'll start being able to piece that together and understand it. But just don't panic. Just stick to our plan that we have. Okay? The extra credit part, right? Extra credit, right down here, right? And I said, what is it? It asks for extra credit. Find the acceleration of point E, right? What is the acceleration of point E? And this one was like, right? Again, this is just above and beyond. If you have time, work on this, right? And it would be what do I know about the acceleration of point E?
Since it's a rolling wheel, you can just treat it as like r omega squared.
Yes, right? The only component there is no tangential acceleration back and forth relative to the ground because that has 0 acceleration in the x direction and it only has an acceleration up towards the middle and it's just going to be the centripetal acceleration which is just r omega squared. So you would have to be able to look at this real quick and be, oh yeah, that the point E has an acceleration of r omega squared. So AE. Right, and this just came from rolling wheel kinematics. If you're able to notice that AE, the acceleration at the base of a rotating wheel is just r omega squared. So it's just going to be equal to negative omega A squared times r A is seen from E. And this is where your vector comes in, right? Or just know that it's in the J direction. You could look at it and know that it's in the J direction, right? So that's it, but what's the problem here? I don't know what omega A is yet. So you have to do a quick little thing to determine what omega A is. Right? So I need to, right? I could take advantage. I know what its velocity is, right? It's 40, sorry, it's not 20, it's 40 to the right there. And so just by inspection, what does it need to be rotating it at? -8, right? If this one's rotating at half the speed, right, at 20 feet per second, right, and this one's, and it has 4 omega, this one over here with the exact same, well, it should be rotating twice as fast as that because its velocity is twice as fast, right? Or just, again, stick to the plan, right, which is, you could say omega A, right, and just using rolling wheel kinematics is -v over r, so it'd be 40 over 5, which is equal to -8 radians per second. Right? And then you put that up above, right? You take that and put it in there. And then, so this ends up being 8 squared times 5 in the J. And so this will end up being 320 in the J direction, and that's feet per second squared. Cool. Right, and that's the extra credit, right? I mean, like you got to do that on the fly. When I'm up here lecturing, I forget every once in a while what I'm wearing, and so And I'm just thinking like, hey, can you take me serious right now? I think you can. Okay, any questions about this one? Yeah? Anders. Yes. What do you got? What did I do?
Why is omega A different than omega AB? What is...
Oh.
Omega A is the
Mm.
wheel itself,
Mm.
rotation of the wheel. Omega B is the bar. And the bar is not actually rotating at all at that exact spot.
Man? Yeah, right? It's omega A. Trying to be clear, and then I sphere my writing, right? Omega A is how the disc on the left is rotating. Omega AB is how the bar in between is rotating. Omega C is what the disc on the right is doing. Yeah, and so that's why I needed to know what this one was rotating at, because E is going to be dependent upon that. The acceleration to E is going to be dependent on that. Is that good, Anders? You got it? Cool. Questions? Concerns? Problems like this in general? Mustache. Yeah.
Like summary your list of other constraints. I feel like that's where I get my
Oh, the constraints.
The process is easy, but like the constraint like at the bottom of the wheel is zero. Like other constraints.
Yeah. No, I hear you. I don't have a list, but let me see if I can come up with my brain. The bottom of a wheel. Oh, you can write this down real quick. Yeah. Bottom of a wheel, the velocity in the tangential direction is zero. Right? Both directions are zero, right? The velocity is zero right at the bottom. So that's the velocities. Accelerations, the tangential acceleration is zero. The vertical component is r omega squared. It's the centripetal that's back towards the middle, right? And it's going to be pointed back towards the middle. So it's just the j component of this. But if it was on the wall, it would be in the I component. It's just back towards the middle of it, right? Because you can have wheels rolling on walls too, right? Ooh, that's a good one. Wheel rolling on a wall. I like this, right? Wouldn't that be good? That'd throw you off. But it's the same. It's just if you need to, just turn your paper sideways, Ed. Right? Just turn your paper sideways.
All the work sideways.
Yeah, just do all your work sideways.
Would you grade it fairly?
Yeah, that's right. Everybody. Simple brains. You gotta use simple tools for simple brains. Just flip it over on the side. Right? I know that because that's probably what I would do. But those are rolling wheel ones. And then, or if it's stuck on a slot or something, right? If it's stuck on if it's stuck on a bar going horizontal, right? Then I know it's only in the I direction. Or if it's going this direction. What would you do if it was on a slant? You turn your paper to meet the slant. What would you do?
You have to have sines and cosines.
You would have a unit vector, exactly. You would have a unit vector that would be pointed in the direction that slant. This is also a good problem. I like this one. There'd be a unit vector, right? If I did something like this, if there was you guys you're giving me all your weaknesses. You're giving me all your weaknesses. This is good, right? If I had like a slot, right? If I had a slot that was like this, right? And my little block was constrained to that slot, and this was X, right? And this was X, and then Y, right? Y was like going this way, right? Right? So then this, you would come in with a constraint that like, VA was equal to, with this angle, it'd be if this was my angle theta, it'd be the magnitude VA times cosine theta in the I plus sine theta in the J, right? Because you'd be constraining it to that unit vector that's pointed in the directions like that, right? This is a great question. I'm not going to be able to do that. What's that? No. I wait till after this, right? I got to flip through the book and find the good ones, right? That makes sense, right? Like you put it in that constraint, and then you follow the same process as you walk through, right? Okay. I think that's all the real constraints there are. Is what I just said there. Yeah. Because you're right. It is the crux of some of these problems. Sometimes is applying that constraint. If you don't have that constraint, then these things, sometimes there's just too many unknowns to be able to solve it. Right? Cool. Ready for the next one? Okay. I think at this point, At this point, I'm stuck wearing this because if I took off this right here, my shirt would be soaked all the way through, which would be good, which would be pretty gross. Would be pretty gross. I won't put you through that. Very warm. Okay, now this is the solution. All right. All right, let's do this one.
I got a question for problems like this.
Yeah.
Are we going to be given, like, on the exam, are we going to be given, like, the eye around, like, a specific axis, or should we put that on our phone?
Nope. So this came. I'll give you something like this at the top.
Okay.
So this. I plucked this right out of the exam. Great question. Right. Do you need to write down all the moment of inertia equations? No. I'll give you any relevant moment of inertia equation you may need. Right. You may or may not need. Right. And so I put in. This is what I put right at the top. Right. I just plucked this right out of your book. Right, so don't worry about that. These guys will be given to you, right? I won't necessarily give you the exact value, but I will give you this, and you can play a matching game and find the one that works for you, right? Okay. So great question. All right. So first part, mass props, right? I got to determine my mass props. So if you want to stick to our, right? We talked about doing mass props, right? I'm going to do this. I like to do when I have a fixed point. When I have a fixed point, I like to do the moment of inertia about that fixed point. Because if you do that, then your reaction doesn't show up in your moment equations, right? It just makes your algebra a little bit easier, right? If you got a TI-89, it doesn't really matter anyway, but because I can just put in 3 equations, 3 unknowns easily. But that's what we're going to end up with. You'll end up with 3 equations, 3 unknowns if you sum the moments about the mass center, because your reaction is going to show up in there. But if you do it about the end point right here, one of the equations just pops out, and the other one, or one of the values just pops out. Alpha pops out without doing a linked equations. Okay, so I'm going to do it about this right here. So I need the moment of inertia of this rectangular disk about its end, like about its corner, right? And so you got to be careful when you read this thing right here. I need it about its corner, right? And so the primes here, those are the moments of inertia about the mass center. So these are the primes about the mass center. I don't want it about the mass center because I just said I'm going to do it about the corner. What I want it about is this Z right here, right? I want the Z coming up because again, we're fixing this thing in the XY plane. So I don't care about the other ones. Later on when we do 3D, we care about the other directions. But right now we're only doing 2D. The only rotations I'm gonna have is about the Z axis. The Z axis I care about is the corner right there. And so I'm looking for IZ. Here is the IZ axis right here. This is the equation that I want to use. I would say a lot of people mess up this just right from the get-go. They mess up what their moment of inertia is, right? I don't want this one, IX axis. I don't want Y axis. I want the Z axis. And I don't want Z prime axis because that's about the mass center. I want it about its end. So that's the one I want. B and H, right? Or that's my B and there's my H right there, right? And so in this case right here, I about O is equal to 1/3 mass. They give us the mass of this thing, right? They give it 30. The 30 is the mass. 30 kilograms. 30. And then my B is 2 and 2. So 2 squared plus 2 squared. Right? And this is equal to 80 kilograms meter squared. Right. Mass center is easy. I don't need to do any calcs for that mass center, right? If you want, I mean, mass center's right in the middle. Hopefully you can see that. Right? Mass center's right in the middle, so I don't really need to do any calcs right there. It's going to be 1 over and 1 down. 1 to the right, 1 down. Okay, so that'll come up a little bit later because I need to know where the mass center's at. Okay, free body diagram. 1. F, B, D. Okay, we draw this thing. It is a I like to use black. Right? Force is acting on this guy. Gravity. You're my designated guy this time, right? Mass times gravity through the mass center. That's key to these problems is your mass, your weight acts through the mass center, right? Which would be right smack dab in the middle. What else do I got? reactions, right? Somebody said that. Right, I got OY and I got OX right here. Okay, and we got one more. What else is missing here? There's a moment. They tell us that we have a moment, an applied moment, right? That applied moment is just kind of in a positive moment, right? It's acting in that direction right there. Right, so we put in all, and they actually tell us that this is 10. Bless you, bless you. 10 Newton meters. Okay. One other thing I always like to put on here is key dimensions, right? This key dimension going down 1. Right? And then it's over 1, 2. Uh-oh. Right. No real angles to do, just that's it. Okay? So my free body diagram should have everything on there. That's an M, this meters there. Okay. So now I'm ready, right? Like I said, just stick to the plan, right? I'm going to do kinematics first, right? I like you can do kinematics afterwards. You're just going to be missing some components. I can write my equations of motion first, or I could do my kinematics first, right? And again, like the way I like to do these ones is like I need to know what AG is doing. That's what I say to myself, right? Really what I need to know is how does AG relate to omega and alpha is really what I need to know. But the way I think of it is like I need to step to AG because AG is something that shows up in my moment equations down below. So that's what we do. We're going to step to AG. Where would be a good place to step to AG from? Point O, because it's not moving, right? Point O isn't moving. Right? So I'm going to take a step from there to there. Right? And what I care about is accelerations right now. So AG is equal to AO plus alpha, which we don't know yet, right? Crossed with R, G is seen from O. Minus omega squared, R, G is seen from O. From O. Okay. Actually, all the problems we've done so far, this thing we've been starting out at rest, right? We said, oh, this thing's starting out at rest. It's not starting out at rest. It has an omega to begin with.
What are those subscripts? Is that a G?
Oh, yeah. I wasn't done yet. If we zoom right, oh, nope, zooming in doesn't help. Oh, yeah, that's G, sorry. G, O. Right, try to be as clear as possible, but then also being scribbling sometimes. Okay? But usually, right, all these problems we've done so far, it's been starting out with omega equal to 0. In this case, omega is not equal to 0. They tell us that we have an omega. We have this 4 radians per second. So this thing is moving at this point. Okay? So let's do it. Let's keep moving through this thing, right? So AG, A naught is 0, right? Acceleration at that point's not moving, so that's 0. Can't move. And so it's equal to alpha in the k direction. I always just assume a positive alpha crossed with our G is seen from O, so I'm going to the right 1. That's 1 in the I direction. And I'm going down 1, so that's 1 in the J direction. Right? I'm taking a step to the mass center from O, so it's going to the right and down. Right? And then I minus a negative 4 squared. And again, it's 1 in the I minus 1 in the J. Right? This is a negative. Right? It's a negative because if I rotate my fingers that way, it's going that way. It doesn't matter. I mean, the sign doesn't really matter, right? Because that value gets squared, right? It's the centripetal acceleration. The centripetal acceleration doesn't care if it's going this way or this way. It'll still have to accelerate back towards the middle. Okay? And that's what this does. This part of it says that this negative and this is saying it's going back towards the middle. It's saying it's accelerating back like that towards the middle. Or I guess, yeah, it's accelerating back that direction. Right? And so anyway, that's taking care of that for us. Right? So you carry this stuff out. Oh, this ends up being AG is equal to alpha in the I plus alpha in the J. That's that cross product. That's this cross product. Minus 16 in the I plus 16 in the J. Okay? And so right? I'm not going to go over those cross products, but make sure that you can get that by doing your cross product, right? K and an I gives me, right? K and an I gives me positive J. K and a negative J gives me positive, no, K and a negative J, positive I. Did it. Okay. Make sure you can do that, right? So then now I lump them, right? I can lump all my I's and my J's. And so I get alpha minus 16 in the I plus alpha plus 16 in the J. Right? So that's what AG is going to do in terms of accelerations. Right? I always like to do this step right here. I say, hey, this right here, this is AGX. Right? This right here, AGY. Right? Because it's the AG, right? It's AG and it's the I component and the J component. That's why that's AGX and that's why that's AGY. And the reason I do that there is because later on, when I write my equations of motion, that's what my forces are going to be equal to. My forces in the X direction are going to be equal to this. Forces in the Y direction equal to this. I like to do that this way, but again, you can think of these things as being extra equations that you can use to solve. We're going to have 3 equations later on, but really there's 4 and 5 equations that we really get to use. Okay? Because there's just too many unknowns floating around. Okay. All right. So now we're ready for equations of motion. Any questions about that step right there? Take a step there. And again, what I'm after is I tell myself I'm after AG, but what I'm really after is the relationship between AG and omega, right? And both of those things, how everything relates to each other. So equations of motion. Equations of motion. Nope. I do black work. Right, so that's what I do. I got 3 I could use. Sum of the forces in the X is equal to MAGX. Okay, so then what I do for the sum of the forces on this left-hand side, I say, hey, I go up to my free body diagram and say, hey, what's acting in the X direction? I got OX. That's it. Okay, that's the only force that I have acting in that direction is OX. So I write that down here. I say OX. OX is equal to MAGX. M is 30. And then AGX, I just take this guy from up here. Whew. Right? I do that. And so this is going to be alpha minus 16. Right? Vectors are gone now because I'm looking the X, Y, and Z direction. So that's one of my equations that I need. Then I sum the forces in the Y direction. That's equal to MAGY. Right? Go over to my free body diagram. Say, hey, what's acting in the Y direction? I got OY going up. I got MG going down. That's all I got. Those 2 things. Right? So that's what I do. I say positive OY minus MG, which is 30 times 9.81. And that's equal to my mass, 30, times alpha plus 16. Okay, that's my second equation. Right? I got one more, and that's sum of my moments. So I come down to that one. Sum of the moments about O, right? And this is key. I got to do it about O because that's what my moment of inertia is about. So that's moment about O. It's going to be equal to IO times alpha. Okay? And so then I look up here. I like to do this, so you can do it with cross products. I just like to go up to my free body diagram and then just use some logic here, right? What's going to cause moments about O, right? OY is not going to cause moments, right? OX are not going to cause moments about O, right? That's what I'm saying. It keeps it out of our moment equation. If I said I'm some of the moments about here, this and this would show up in my moment equation, which is fine. You could do it that way. But if it's a little cleaner to do it about O. And so really the only thing causing a moment that can cause a moment is mass times gravity and their applied moment, right? And so the mass times gravity is going to do, right? Again, it's just going to be this force times this perpendicular distance, right? Which is just 1 meter. So that could be a positive moment or a negative moment. That gravity term is going to cause a negative moment, right? Because it's going to make it rotate like this, and my thumb's going into the board, so it's going to be a negative moment. But then the applied moment, is that a positive or negative? The applied, it's positive because it rotated like that. It's positive coming out, right? So that's what we do. So we come down to our moments here, right? And I say, I got a positive 10. That's my applied moment, minus 30 times 9.81. That's the magnitude of my gravity force, right? And then I multiply that by 1 because that's the moment arm. It's negative because it's making it rotate the other direction, right? Right? It's only that perpendicular distance that causes that moment. And that's equal to this 80 times alpha. 80 alpha. Right? And so there they are. Right? My 3 equations and 3 unknowns. The unknowns are OX, OY, and alpha. Right? And so I think up here too, I think I said, right? What are the reactions at O and what's the alpha of the plate? So it makes it look like there's 2 problems, but they're the same problem, right? We solve all 3 of those at the same time. And what you get, you solve those 3 equations, we get alpha equal to negative 3.55 rads per second squared. I get OX equal to negative 586.6 newtons, and OY equal to 667.69 newtons. Right? 6.7. That's great. Thank you. Thank you for pointing that out. That one wasn't even on purpose. Right? And then again, I like to just do a little stink test, see if it works, if that's what it's supposed to do. Should the alpha be negative? Yeah, right? Because it's rotating down like that, right? It's going like that, right? So it should be alpha, so that makes sense. It's OX, right? OX says it's negative, right? So that's an important thing to note, right? I said OX was going that way, right? I didn't know, so I just said it was going to the right. Is it going to the right? No, it's going back to the left, right? And that's okay. That's okay for that to happen. That's what that negative means. It means it's not going the direction I assume. It means it's going the other direction. So it's going back that way, right? And does that make sense? Should it be going back to the left like that? I would think so, right? Because the centripetal acceleration, right? It needs to hold that thing. It needs to get it to go back towards the middle because of centripetal acceleration. And so it should be back to the left. So it's negative 586. And then OY should definitely be up. All right, so 667. All right. Any questions about that one? If you did it about the mass center, let me just show you. Right, if I was going to do it about the mass center, mg, just because it's all right to do it, there'd be a negative OY times 1 minus OX times 1 plus 10 would be equal to IG times alpha. This is what I'm saying. This is what I'm saying. Is if I sum the moments about the mass center, I would have, right, this guy, right, is causing a moment about there, and that's going to be negative, right? This guy would be causing a moment about the mass center. That 2 would be negative, and so that's why both of these are negative, and then I add on the 10 is equal to IG times alpha. So I would have to get what IG was, which would be the Z prime. The Z prime in the previous table is what the moment of inertia is that you would use. And so then when you did this, right, from this, I could solve for alpha directly, right? The only unknown in this equation is alpha, so I could just solve for that, and I take that alpha, and then I put it in here. For those of you that don't have a nice calculator, you would want to do it that way. Otherwise, OX and OY are in all 3 equations, and so truly it is a simultaneous, you'd have to do substitution and work your way back, and it's just the algebra ends up being a little more difficult. Okay, extra credit. Anybody try and successful with the extra credit on this one? Nobody tried it? Did anybody try these problems beforehand? Good. Bill Nye did. You all right? You right, Isaac?
What?
You all right? Still doing okay? Okay. I'm not gonna do the whole thing, but also you have to do work energy. You have to do work energy. And so this isn't on work energy, so then maybe you wouldn't have seen it, but that's why this one was extra credit, right? I need to figure out what the omega is at the bottom, right? It's gonna show up, it'll show up in my equation, so I need to figure out what omega is at the bottom. And so you have to do you have to do this, right? Because it gets too complicated. If you tried to do this with like integration with alpha, alpha's not constant. Alpha's changing with angles as you go down, and it would get pretty complicated. So yeah, you got to do work energy, right? And so it starts out with kinetic energy at the top and potential energy at the top, and there's work being done from state 1 to state 2, and it's all going into kinetic energy down at the bottom. And so you got to do a little algebra for it tilted over on its side. You have to do a little bit of that. And then you got to, work your way through, and you can figure out what the omega was at the bottom. It ends up being 4.36 radians per second. And then you go back and you do your AG again, but now your kinematics is changed, right? On your position vector that you have, it's just going to be going down. It's going to be the 1.41. And then you just, same equations kind of down below, and out pops what the answers that I gave you. So if you did want to look at this, you could do it, right? Like I said, I'm recording this. I'm going to post it on YouTube. You can go back and look at this if you want, or you can quickly take a picture of it if you wanted to, and get that solution. But that's all I'm going to go through right now. Yeah, there are questions or concerns, or yeah.
What's the secret password?
Oh, there was a secret password. Yeah, I used to do that it was like if you attended class, I would give a secret password and then you'd put it on here. But now we're doing the wheel of death, if you will. And so, what if we did it? We're like, I need to come up with a reward. I really do. I've been saying that forever, but some sort of reward. Piece of candy. I got a bunch of candy left over. I don't bring candy to class. I eat it all though. So, any other questions? Concerns? Interesting. You guys will be just fine, right? Remember, stick to the plan. Stick to the plan. We've got a nice plan for all this stuff. Eat it. Please take the pizza. Eat more pizza. Leave the candy. I'm going to start bringing it to class. Sure? Thanks, guys, for coming, and thanks for dressing up.
Can I ask you a question? Sure. It was the second problem there.
Yeah.
I was just wondering, and I don't know if it makes